As we begin section 5.2.2, it's important for us to remember why we're here. You may recall that at the end of the last section, when we were taking a look at calculating definite integrals, using that limit definition, the limit of the Riemann sums, the number of rectangles went off to infinity, we found that sometimes the setup of that limit was extremely difficult, or at least it produced something extremely difficult to evaluate. And so our goal was to try to, in this section and the sections to come, to see if we can come up with anything new that would allow us to maybe more easily and quickly evaluate definite integrals. And remember again, when you hear the words definite integrals, you should automatically be thinking or translating that into area under a curve. And with that in mind, we'll see here that in this section, we're going to take a look at a lot of different properties of definite integrals, or properties of areas under curves. And if we take a look at what the theorem states here, we'll see that we have 7 different properties coming right off, just right from the start. Now, many of these properties are actually really simple to see and to understand if we recognize, again, that each of these are just trying to reference something about an area under a curve. Let's take a look at what the theorem says. Suppose that f and g are integrable functions, meaning I can find the area under them on the interval from a to b. Then we should be able to state the following. Well, number 1, an integral of f from a to a should equal 0. Okay, well, let's again try to think about this as a property that would be true about an area underneath a curve f of x. So if I have a curve f of x sitting out in space that looks like this, and I try to find the area under it, starting from a and going over till a, so that as I'm just looking at this right here, how much area have I shaded in red? Well, it's no surprise that that area should be 0, because notice I haven't stretched it all to the left or to the right. So if I was to ask how thick or wide that red area is, technically it has no width, right? Because it's occurring at a single point. So again, this property here makes a ton of sense if I think about it as an area under a curve. Now, if I take a look down here at this next property, this one's a little bit harder to see, but we can still talk through it. Let's suppose that I was going to go ahead and try to find the area underneath the curve f of x from a over to b. Okay, so I would have some sort of a picture that looks something kind of like this. Here's my function and an area from a to b. Notice that this second integral over here has my bounds occurring in the reverse order. I'm starting at the value of b, and I'm kind of moving backwards towards the value of a. And if this happens, what I'm going to end up with is a negative of the same amount of area. So the areas that I end up with here are just going to be negative amounts. Now, the reason for this actually corresponds to our calculations for our widths of our rectangles. Notice that in the first interval, or the first definite integral that I have over here, I calculate the width of my rectangles by doing b minus a over n. This top bound minus my bottom bound over n. And of course, this is going to generate something positive since b is a larger value than a. However, in this second integral here, let's call this delta x number 2, I'm going to end up calculating a minus b over n, because I'm going to be doing my stop value minus my start value. Notice what this is going to do then is generate almost the exact same value here, but negative. So like if this was 5 minus 2, I'd have 3 over n. But if it was 2 minus 5, I'd have negative 3 over n. When I reverse the order of the bounds, I'm essentially changing the width of every single rectangle to a negative width, which is ultimately going to change the area. Any area that used to be positive would now be negative, and any area that used to be negative would then become positive. So essentially I get a complete reversal on the size of the area. That's an interesting property. Let's take a look here at property number 3. This one here is also very easy to see with a simple picture. Let's suppose that I have a function that's f of x equals c, so it's a constant. Well, we know that constant functions just look like nice horizontal lines. So if I was to go ahead and think about grabbing the area underneath this curve from a to b, notice I don't even need calculus to answer this question because the shape of my area is a nice little rectangle. Notice the vertical height for this is c, and the distance left to right is b minus a. So I can actually measure the actual side lengths here, and so my area should be b minus a times c. And look, that's exactly what we have. Similarly here, if I have a function and I'm trying to integrate it, but it's being multiplied by a constant, I can take a constant outside and just find the area underneath the original function. This is actually coming from a property of limits, where you might recall that we can take a limit outside, a constant outside of a limit. Number 5 and number 6 are also fairly easy to remember because they also look like some derivative rules as well as some limit rules that we've been working with this semester. If I'm trying to integrate the functions of the function f plus g, I can separate that integral into two separate integrals, finding the area under the first curve and then finding the area under the second curve. And I can do the same thing with subtraction. Property number 7 is the last kind of interesting property to take a look at, and it works in the following way. It looks complicated at first, but notice that it's saying, let's suppose I'm trying to find the area under a curve going from point A over to point C. Well, notice that if I wanted to find this area here in the picture, I would know that it would look like this, right? I'm looking at this red space. Okay, well this says what you could do is instead of finding the area from A to C, you could find the area first from A to B. Well, let's suppose that B is right here. If I found the area from A to B, that would be just finding this green space, and that's obviously not equal to the red space. However, if I then found the area from B over to C, which would maybe be something like this space, I could see that the blue area plus the green area is the grand total of the red area. So what this is really allowing us to say is that if I'm kind of making a trip from A over to C, right, I'm adding up all the area along the way, you can always kind of take a pit stop anywhere along the route, right? You could just decide, oh, gotta go all the way from A to C, how about I just stop after a little bit and I'll just add those two pieces together. The interesting thing about this property, though, is that what you'll notice is it doesn't actually say anything about where B is located in relationship to A and C. And so even if I actually had a setup here that was A to B like this, I could still see that if C was maybe somewhere in the middle, I could recognize that this property is still going to hold true. Notice that my red area from A to C is still going to be equal to my green area from A to B, which is obviously a much larger area, but then add on the area from B to C. Well, notice B to C is requiring me to go in a backwards direction, which makes property 2 kick in, which means that the area from B to C in this backwards direction will be considered negative. It's almost like I'm taking that green area and I'm subtracting the blue space. And of course, that leaves me with the red space. So the important thing to note here with all of these properties is that they are understandable. They don't just have to be some sort of like cryptic set of symbols that you dedicate to memory. You really need to make sure that you do understand them. And that might mean that you have to kind of revisit these pictures time and time again to make sure that you kind of can visualize what's happening with each of these properties. So it's very important that we understand what these properties are and why they are what they are. And we'll see how we begin to use them in other examples in this section.